Hey there, deep divers, and welcome back. Science is about facts and evidence, right? What if that's not the whole story? Let's explore the psychological games, hidden pressures, and forbidden fields that might be holding back the future of discovery. Today, we're exploring Alternative Science, Challenging the Myths of the Scientific Establishment by Richard Milton. Before we plunge in today, if you're digging what we do here, unpacking the fascinating, the overlooked, the downright mind-bending, do us a solid, hit that like button and subscribe.
Yeah, it really helps other folks find these deep dives.
It really does. Okay, so picture this. 1803, rural France. It's not rain, not hail.
Nope.
But thousands upon thousands of rocks are plummeting from the heavens, just scattering across fields, terrifying the locals.
Imagine seeing that.
Right.
Yeah.
Now, your first thought might be, okay, rocks fell from the sky, case closed. But the esteemed scientific minds of the time.
Oh, they basically rolled their eyes.
Totally. Dismissed it as folklore, peasant tall tales. It actually took an official investigation, like a proper deep dive of their own, for them to finally admit, whoa, okay, space rocks, they're a thing.
Which really gets to the heart of it, doesn't it?
Exactly. Which brings us to the really juicy bit.
Yeah.
How does anyone figure out when a seemingly crazy idea is actually the next big thing and when it's, well, just plain crazy?
That's the cosmic question. And what's truly captivating is this inherent tension within science itself. It's a system built on questioning, right? On rigorous proof. Yet it can also show this remarkable resistance to the truly novel.
Like with the meteorites.
Exactly. The meteorite story is a perfect microcosm of this, the universe literally dropping evidence on their heads. And still, the established worldview initially just couldn't process it.
Precisely.
Our mission is to unravel the threads of why science, in its institutional form, can sometimes put up these barriers to fresh perspectives.
And explore the stories, right? The compelling stories of those who dare to challenge the accepted wisdom.
And to map the often surprising, sometimes really circuitous routes that true innovation takes.
Think of it like getting the inside scoop on scientific revolutions, the behind-the-scenes drama, the moments of doubt, and eventually those "you were wrong" triumphs. We'll be hitting everything from like the seemingly preposterous idea of heavier-than-air flight
all the way to the enduring enigma of cold fusion.
So settle in, because this is going to be an intellectual adventure. Okay, let's get into it.
Okay, let's start by really examining this inherent resistance we've touched on. As that meteorite example shows, the scientific method, its emphasis on evidence and testing, it acts as this crucial filter.
Yeah, keeps the nonsense out, hopefully.
Right, against what we might call unfounded beliefs. However, this very essential rigor can sometimes become a really formidable obstacle to genuinely groundbreaking ideas that just don't yet fit within the existing frameworks.
Right. The book throws us straight into this with Carl Reichenbach. Now, his name might not ring a bell for everyone.
Probably not.
But he serves as this potent symbol. Here was a dedicated scientist exploring, totally uncharted territories, yet his findings were met with just significant skepticism.
It's almost like the scientific community has this natural defense mechanism against anything that seems, too far outside the box.
That's a great way to put it, a defense mechanism.
And we see this pattern echoed throughout history. You think about Michael Faraday, right?
Yeah.
One of the absolute giants of 19th century physics.
Electromagnetism.
Exactly. When he unveiled his discoveries about electromagnetic induction, a truly revolutionary concept that underpins so much modern tech, he also faced considerable skepticism from his peers.
Wow, even Faraday.
Even Faraday. It's a humbling reminder that even the most brilliant minds can hit that wall when their insights challenge the established scientific understanding.
It really makes you think about the tightrope walk science has to do. We absolutely need that robust process, that scrutiny, to prevent, let's say, less than well-supported notions.
Definitely.
But then how do we make sure we're not accidentally stifling a potential Einstein or dismissing a future Faraday just because their initial ideas don't neatly slot into the current dogma?
This is such a core tension that the book highlights really astutely. It raises these fundamental questions about the gatekeepers of scientific validity, like who gets to define what counts as sufficient evidence.
Right, and whose voices get amplified, especially in publicly funded research where huge sums are involved.
And how can dissenting scientific views actually be heard and evaluated fairly? These aren't just, abstract philosophical questions. They have really profound implications for where science actually goes.
Absolutely. The book doesn't really pull any punches in its critique of what it calls big science. It sort of paints this picture of a scientific establishment that, well, in some ways, could be vulnerable to becoming its own kind of echo chamber.
Where unconventional ideas get quietly sidelined.
Or not so quietly, sometimes, yeah.
The book uses a pretty strong analogy here, drawing a parallel to a banana republic dictatorship. Now, obviously, that's not meant literally, but it serves to underscore concerns about the potential for a lack of accountability when enormous amounts of funding are involved and maybe when the channels for independent critique are limited.
Right.
It draws the sharp contrast between, say, the public scrutiny applied to royal spending or other big government things.
Yeah, people notice that stuff.
And the relative lack of oversight regarding the actual value and direction of these massive scientific research budgets.
That's a provocative point, isn't it? We might argue about the cost of, I don't know, a new highway project. But do we apply that same critical lens to the billions spent on scientific research? The book argues that, well, as things stand, there's a significant gap in how the value and the impact of this huge expenditure are really assessed by the wider community.
And this lack of sort of readily accessible ways for the public to check in beyond just administrative oversight is a key concern the book raises.
Yeah.
It suggests that until we develop more robust ways for society to evaluate the return on investment and the overall direction of science, we can't be totally confident that these substantial resources are being used in the absolute best ways.
Okay, so we've set the stage. Science, our ultimate truth-seeking machine, can sometimes be a bit resistant to installing new software updates, let's say.
Hey, good analogy.
Now let's dive into some really astonishing examples, groundbreaking innovations that were initially met with just massive skepticism, often for the very experts you'd think would be cheering them on. First up, powered flight.
Ah, yes, powered flight. A classic illustration of how deeply entrenched expert opinion can just clash with determined ingenuity. The book highlights that just weeks before the Wright brothers' big flight at Kitty Hawk, this highly respected professor, Simon Newcomb, mathematics, astronomy, Johns Hopkins,
Big name.
he published this seemingly definitive article scientifically proving, and I quote, that powered human flight was utterly impossible.
Utterly impossible. Just think about that. Here you have two bicycle mechanics in Dayton, Ohio, quietly working away.
Tinkering in their shop.
While the esteemed academics are basically declaring their efforts doomed by the laws of physics.
Yep.
And Newcomb wasn't alone, was he?
Not at all. Rear Admiral George Melville, chief engineer of the U.S. Navy, he chimed in too, dismissing attempts at flight as simply absurd.
Absurd.
Exactly. And fueled by these kinds of authoritative statements from, the top scientific and military minds.
Yeah, people listen to that.
The established scientific journals and the mainstream press, even big ones like Scientific American and the New York Herald, openly ridiculed the Wright brothers, called them delusional, hoaxers.
It's almost darkly comedic looking back. These guys in Dayton are actually flying their machine,
Getting off the ground.
achieving sustained, controlled flight, and the local papers in their own hometown are stubbornly refusing to even report it. You'd think seeing a machine fly would be front-page news.
You would think! But the prevailing scientific view was so fixed that even credible eyewitness accounts just couldn't get any traction.
So what broke the dam?
Well, it wasn't until President Theodore Roosevelt himself, seeing the potential military side of things, ordered public trials in 1908.
TR.
That's when the Wright brothers finally got to unequivocally show everyone, look, this thing flies. It forced the U.S. Army and the skeptical press to finally admit, okay, the age of aviation is here.
Wow. It's a powerful reminder that sometimes seeing isn't just believing. It's the only way to shatter those deeply ingrained but wrong scientific ideas.
Absolutely. From the skies to the seas now.
Let's do it. The need for speed. The book tells this great story about Charles Parsons and his revolutionary turbine engine. He saw ships going way faster than anyone thought possible.
Parsons' journey is another one of these compelling narratives of innovator versus the status quo. Even though he came from a privileged background, he faced huge hurdles convincing the British Admiralty about his turbine engine for warships.
What was their problem?
They politely but firmly just dismissed his proposals. They confidently asserted that going faster than, say, 20 knots was simply impossible.
Impossible again.
And that any ship with his crazy new turbine would be inherently uncontrollable.
Uncontrollable. Imagine telling the inventor his engine will cause chaos. But Parsons wasn't easily put off, was he?
Thankfully, no. He realized, okay, talking isn't working. I need a dramatic, undeniable demonstration, something they can't ignore.
And he delivered.
Oh, did he ever? At the huge Spithead Naval Review, like the whole world's naval power is there watching. Parsons' revolutionary ship, the Turbania, just appears out of nowhere.
Zooms past everyone.
Utterly outpaces the Royal Navy ships chasing it. Hits an astonishing 34 knots, nearly double the speed of anything else afloat. It was this jaw-dropping moment, witnessed by everyone that mattered.
I bet.
And it instantly catapulted his invention into the limelight.
Talk about a mic drop moment at sea.
Yeah.
Suddenly, every navy, every shipping company wants turbines.
Exactly. By 1905, the trip across the Atlantic to Canada was cut down to just 5.5 days. And by 1910, the Turbinia's successor nabbed the blue ribbon for the fastest Atlantic crossing.
So from impossible and uncontrollable
To absolutely indispensable technology, revolutionized navies, revolutionized shipping, all thanks to Parsons not taking no for an answer.
Amazing. Okay, shifting gears from war at sea to lighting up our homes. Thomas Edison and the light bulb.
Edison. A household name for a reason. But it wasn't easy. Loads of inventors tried to make a practical electric light before him, but none made one that was reliable, lasted long enough, or was cheap enough for everyone.
Right, it needed to be practical.
Exactly. Edison, with his amazing research lab at Menlo Park, New Jersey, like the first real industrial R&D facility.
Yeah, the invention factory.
He tackled the challenge head-on. And his vision wasn't just a light bulb. He wanted a whole system of parallel electrical lighting. So if one bulb went out, the whole street didn't go dark.
Smart. And when he cracked it,
He staged this absolutely spectacular public demonstration, lit up the streets, the buildings of Menlo Park with electric light for the first time. Breathtaking. People traveled for miles just to see it.
you'd think the scientific community would be thrilled.
Well, the reaction was notably subdued, shall we say.
Oh, yeah.
The book points out that not a single prominent scientist accepted Edison's personal invitation to come see his invention working. Even Professor Henry Morton, a respected physicist who lived nearby and knew Edison,
Could be bothered.
couldn't be bothered to make the short trip.
Yeah.
Instead, he felt the need to publicly denounce Edison's achievement as a conspicuous failure and a fraud upon the public, all in the name of upholding true science.
Wow, just wow. A fraud upon the public.
It's a stark illustration, isn't it? The gap between massive public excitement for real innovation and the often cautious, sometimes downright dismissive stance of the established scientific order. Even with the undeniable evidence shining brightly, some scientists just clung to their disbelief.
And finally, in this tour of initially dismissed wonders, let's touch on television. John Logie Baird.
Baird. He toiled away for years in his little lab in Frith Street, London, just relentlessly working to send moving images through the air.
A pretty wild idea back then.
Totally. He had his first big public demo, but to avoid industrial espionage, he cleverly kept the transmitting gear hidden. He just showed the scientists and pressed the receiving set.
And did it work?
According to the Times reporter who was there, yes. A recognizable human head speaking appeared on the screen, a bit faint, maybe a bit blurry sometimes, but it was there.
Now, the book admits it wasn't exactly HD.
Oh, definitely not. His early electromechanical system had limitations. But even as critics generally agree, his pioneering spirit, his relentless work, was crucial for Britain launching the world's regular public TV service in 1936.
But he faced skepticism too.
Absolutely. And the book stresses it wasn't just about the technical limits. Some members of the Royal Society, the bastion of British science, publicly called him a charlatan. They questioned if his invention was even useful or feasible.
A charlatan. It really hammers home how resistance to new ideas can be so deeply ingrained, often driven by more than just rational technical stuff.
It really does. It's sobering to think how many other potentially world-changing discoveries might have just vanished because of that kind of intolerance or misplaced skepticism.
Which neatly brings us to our next truly mind-bending chapter, the long, complex, and still pretty controversial saga of cold fusion.
Right, cold fusion. Now, the quest for hot fusion power harnessing nuclear fusion has been this huge, decades-long, multi-billion-dollar scientific effort.
Let's try to copy the sun, basically.
Yeah, essentially, yeah. Replicating those extreme conditions inside stars, immense pressure, millions of degrees Celsius to force hydrogen atoms to fuse and release massive energy. A huge challenge.
So imagine the shockwaves when, in March 1989, Martin Fleischmann and Stanley Pons, two respected electrochemists, mind you.
Not nuclear physicists, importantly.
Right. They announced they've apparently achieved cold fusion. Nuclear fusion happening in a simple electrochemical cell, at room temperature.
It sounded like the ultimate energy dream come true. Limitless, clean, safe power from basically heavy water and palladium.
The initial reaction must have been insane.
Oh, total global euphoria.
Yeah.
Cheap, clean, endless energy. It was revolutionary. But that initial excitement was incredibly short-lived.
What happened?
Prestigious research institutions worldwide, especially MIT Massachusetts Institute of Technology, jumped in to replicate it. And within months, the scientific tide turned dramatically against Fleischmann and Pons.
MIT took a lead role in pushing back.
A very vocal one. Their Plasma Fusion Center, which, interestingly, got a lot of funding for conventional hot fusion research. They quickly claimed the neutron levels reported by Fleischmann and Pons were way too low for real fusion. They suggested the signals could have been none at all, maybe just an instrumental artifact.
Basically saying their equipment messed up.
Pretty much. And this quick, highly publicized dismissal from a powerhouse like MIT was a massive blow to cold fusion's credibility in the mainstream scientific world.
And that had lasting effects.
The book argues yes. It contends MIT's success in effectively killing off cold fusion research is still felt today. Points to the U.S. Department of Energy refusing federal funding for it for years, and the U.S. Patent Office using that early negative MIT report to reject countless cold fusion patent applications.
Wow. Hundreds of applications rejected based on that early report.
Hundreds filed, many rejected, citing that MIT work, despite ongoing research elsewhere.
But here's where the story gets really weird, right? The book dives into some serious allegations about that MIT report itself.
It does. It raises the disturbing possibility that the report wasn't as straightforward or objective as it seemed. That there might have been a deliberate, maybe unspoken effort at MIT's Plasma Fusion Center, not just to discredit cold fusion, but maybe even to, well, manipulate their own research findings to do it.
Manipulate data. That's a huge accusation against a place like MIT.
It was massive. The MIT study, led by Ronald Parker and Richard Petrasso, had two parts. One tried to replicate Fleischmann-Pons using heavy water, and those results did seem to show inexplicable excess heat, more energy coming out than going in.
Okay, so that supports cold fusion.
Potentially. But the second part used ordinary light water as a control. Now, according to standard nuclear theory, if that cell produced significant energy, it would suggest a chemical reaction, not nuclear fusion.
Right, so what happened with the control?
This is where it gets murky. The book details claims that when the figures were released, serious questions popped up within MIT about their accuracy and how they were presented. Allegations of asymmetric shifting of data curves, questionable removal of the entire steady-state signal from key graphs.
Whoa, that sounds like more than just standard data cleanup.
Way beyond accepted scientific data reduction, according to the critics. And these serious allegations caused major internal dissent at MIT.
Someone spoke out.
Eugene Milov, a highly respected researcher and editor at MIT's Lincoln Lab. He got deeply troubled by what he saw as deliberate distortion of the data. He eventually resigned from MIT and publicly accused the institution of publishing deliberately fudged results specifically to discredit cold fusion.
That takes guts. Was he alone?
No, Dr. Mitchell Schwartz, another researcher who looked closely at the MIT data, later published an independent analysis backing up Milov's concerns. He concluded the data had indeed been improperly manipulated.
That's just a stunning indictment.
Yeah.
But the cold fusion story didn't just die there, did it, despite all that negativity?
No, it didn't. The book highlights that significant investment continued elsewhere. Japan's government, through MIT, announced a big 5-year, $25 million research program.
Wow, $25 million is serious money.
And millions more kept being invested by the U.S. Electric Power Research Institute, EPRI, and a group of U.S. utility companies.
So not everyone bought the dismissal.
Clearly not. This ongoing, substantial funding suggests some in the scientific and tech communities weren't convinced by those initial harsh critiques. They were actively exploring cold fusion for power plants, even smaller units for homes and businesses.
So even as some big names were shouting impossible, others were quietly investing millions to make it happen.
Precisely. It leaves you really wondering where the truth lies, doesn't it? The clash between that initial global buzz, the swift hammer down from some institutions, the serious data manipulation claims, and then this continued quiet investment. It's a fascinating, if unsettling, picture of how science sometimes handles truly disruptive ideas.
It really is. And this resistance isn't just in physics, is it?
Not at all. As we'll see next, it extends into other scientific areas, often with equally surprising and, well, thought-provoking results.
Okay. Let's venture into territory that often gets, well, raised eyebrows. Paranormal metal bending. Professor John Hasted.
Right, Professor Hasted, a respected physicist at Birkbeck College, University of London. He embarked on these really rigorous scientific experiments to investigate claims of paranormal metal bending, the kind often linked to people like Uri Geller.
But under controlled conditions.
Very controlled, often with professional magicians and other scientists watching to rule out any normal trickery or sleight of hand. That was crucial.
Okay. And the book mentions Geiger counters. How do they fit in?
That's one particularly fascinating set of experiments. Hasted used a standard Geiger counter, detects ionizing radiation first to make sure the test subject didn't have any radioactive stuff on them that could mess things up.
Makes sense.
They measured background radiation levels, did control tests to make sure just bumping the device or whatever couldn't cause weird readings. Really careful setup.
And the results?
Under these strict conditions, the subject reportedly could produce abnormal pulses on the Geiger counter, seemingly just by concentrating.
On demand?
Apparently. The book details one instance where the subject, showing signs of intense focus, allegedly made the needle jump to 50 counts per second for 2 whole seconds, with the characteristic pip sounds of radiation detection.
50 counts per second is significant, right?
It's way above background. But it gets even stranger.
Oh.
In a later session, with just Professor Hasted and the author Arthur Koestler present, trying to maximize focus, minimize distractions, they tried to get an even stronger effect. And reportedly, within just 3 minutes of the subject concentrating,
Yeah.
the Geiger counter reading went completely off the scale, potentially hitting maybe 200 counts per second. A totally unexpected result that just defied conventional physics.
Okay, that's hard to explain conventionally.
It certainly is. Now, skepticism is vital in science, prevents wasted effort, sloppy work.
Yeah, gotta be careful.
But these experiments, done by a reputable physicist in a lab, raise compelling questions about phenomena outside our current understanding. The book rightly points out that historical skepticism, while often well-meant, has sometimes been badly misplaced and isn't always a reliable guide in these frontier areas where we just don't know everything yet.
And speaking of areas where our understanding might be incomplete, the book talks about Giorgio Picardi and weird things happening with water chemistry.
Yes, Picardi, director of the Institute for Physical Chemistry in Florence. He got intrigued by these inexplicable inconsistencies in what should have been simple, predictable chemical reactions in plain old water.
Like what kind of inconsistencies?
He noticed the rates of these reactions seemed to fluctuate unpredictably. Sometimes the reactions just wouldn't happen at all, even when everything seemed identical.
Strange.
Then he made a key discovery. If he consistently shielded his experiments with copper sheeting, the erratic fluctuations seemed to stop, and the reactions proceeded as expected.
Copper shielding. So something external was interfering.
That was his hypothesis. He and his team then launched this massive series of experiments, meticulously documenting these subtle but persistent variations. Their findings strongly suggested that water itself wasn't just an inert solvent, but was somehow susceptible to some kind of subtle, pervasive external influence.
Like electromagnetic fields or something.
That was the leading idea. And crucially, his groundbreaking work suggesting water sensitivity to EM radiation or other subtle factors was independently repeated and confirmed by teams at Brussels University and the Atmospheric Research Center in Colorado.
Okay, replication is key.
Absolutely. And the U.S. team refined it further, showing it really was the water itself, not the other chemicals, that showed this weird sensitivity to external fields.
The implications of that are potentially huge, aren't they?
Enormous. The book nails it. If ordinary water, the medium for nearly all biochemical reactions essential for life, is affected by subtle electromagnetic influences,
Then living things, being mostly water.
are almost certainly subject to these currently largely unknown and unquantified influences, too. It really forces a rethink about how biological systems work at a fundamental level.
It really does. And the book gives another example of discoveries hiding in plain sight. Something about a schoolgirl.
Yeah, quite striking. As recently as 1975, a sixth form student, like high school in England, just messing around in her science class, independently rediscovered the constant pull solenoid.
What's that?
It's a fundamental, relatively simple electromechanical device. But incredibly, it had somehow been completely overlooked by generations of scientists and engineers since Michael Faraday's time in the early 19th century.
Seriously? Overlooked for that long?
Apparently so. And this seemingly minor rediscovery is now a key part in hundreds of different devices, worth a lot commercially. It's just a powerful reminder that major discoveries aren't always in complex particle physics or distant galaxies.
It'd be right under our noses.
Exactly. Waiting for someone with a fresh perspective and inquisitive mind to spot them.
So these examples really back up the book's main point, that significant discoveries are likely still out there, maybe hidden in plain sight, accessible to anyone with a truly inquiring mind, regardless of their fancy degrees or lab affiliations.
Precisely. It's quite an encouraging thought, actually.
Okay, now we're really heading into the deep end. Territory that often gets, let's say, strong reactions. The realm of the impossible. Uri Geller.
Ah, Geller. His claims of psychokinesis, mind over matter, and telepathy have certainly stirred the pot. Reactions range from fascination and belief to total skepticism and accusations of trickery.
The spoon bending, mostly.
That's what people know, but the book meticulously highlights that Geller has been extensively recorded on video, in many controlled lab settings, often watched by professional magicians, people who know how to spot deception, and physicists, other scientists.
And crucially,
In many experiments, he reportedly produced anomalous effects without using his own materials or having any prior access to the setups.
okay, that's different from a stage show.
Very different. The book details at least half a dozen distinct sets of controlled experiments at reputable institutions. Stanford Research Institute, SRI, in the US, King's College London, Birkbeck College in the UK, and some results were far more compelling statistically than just bending spoons.
Like what?
The SRI experiments in the early 70s by physicists Hal Puthoff and Russell Targ are key. Rigorous double-blind protocols, neither the experimenters nor Geller knew the target info beforehand, and Geller was watched constantly for any funny business.
And the results were?
Improbable.
Highly improbable by chance alone. One experiment. A standard die in a sealed metal box shaken, put on table.
Yeah.
Geller's job. Guess the number facing up inside the sealed box? 10 times. He passed twice, but the 8 times he guessed.
Let me guess.
Correct. Every single time. The odds against that happening by chance, about 1 in a million.
1 in a million, okay. Statistically, extremely unlikely to be chance. Another SRI test. Guess the contents of 12 sealed, opaque aluminum cans, unknown to everyone. Again, results were statistically significant, way beyond random guessing.
These experiments, under strict protocols, they really challenge our standard understanding of what humans can do, sensory-wise or otherwise.
I absolutely do. And it wasn't just guessing. The book describes Geller reportedly making the digital readout on a sensitive electronic scale go up and down, heavier and lighter, without touching it at all.
Witnessed by scientists in a lab.
Documented. These aren't just anecdotes. They're reported observations in controlled settings using scientific instruments. Difficult to just dismiss as stage magic.
And the Geiger counter incident again?
Yes, at Birkbeck College. Concentrating on the instrument, he allegedly made the needle deflect significantly, hitting levels normally, meaning dangerous radiation, with the pips escalating to a wail, and even a scream as the count rate shot up.
Okay, that's specific and hard to explain away easily.
It is, and the book reminds us observing psychokinetic-like stuff isn't totally new. It references work with an Austrian subject, Rudi Schneider, back in the 1930s. Numerous experiments, strict controls in Britain and France, reportedly producing paranormal events documented by researchers then.
So there's a history here.
A documented, if often ignored, history. And more recently, to support this idea of micropsychokinesis, subtle mental influence, the book starts a big meta-analysis by Dean Radin and Roger Nelson.
What's a meta-analysis?
They statistically combine the results of a large number of previous parapsychology experiments looking at mind-matter interactions. Their conclusion: incontestable evidence for micro-PK.
Incontestable. Strong word.
Very. The calculated odds against the results being just random chance were estimated at 1 in 10 to the power of 35.
10 with 35 zeros after it. That's astronomically small.
Vanishingly small. Radin and Nelson even calculated you'd need a hypothetical file drawer stuffed with 54,000 unpublished negative studies to statistically cancel out their findings.
54,000 failed experiments hidden away somewhere.
Yeah.
That seems unlikely.
It directly challenges the idea that these effects are purely imaginary or just publication bias.
So these various investigations, even if they face skepticism, strongly suggest there might be phenomena current science doesn't fully grasp, warranting more open-minded, rigorous study.
Exactly. It's about inquiry, not immediate acceptance or dismissal.
Okay, from mind over matter to maybe life energy. Let's talk biological energies and fields, starting with mitogenic rays and Alexander Gurevich.
Gurevich, a Russian biologist back in the 1920s. He made this intriguing observation with onion root tips. He noticed cell division seemed to be stimulated when one root tip was near another, actively dividing one.
Okay, how did he test that?
Ingenious experiment. He pointed one growing root tip towards another, but separated them with a thin quartz glass tube that had just a small exposed area.
Like a little window between them.
Exactly. And he found the rate of cell division in that exposed area of the target root tip increased by about 25% compared to controls.
Wow, so something was getting through the quartz.
That was his reasoning. Some kind of radiation from the source root tip. He then tried blocking it with different materials.
What worked, what didn't?
Thin sheets of ordinary glass and gelatin blocked the effect, but a thin sheet of quartz glass didn't.
Ah, and quartz lets UV light through, but regular glass blocks it.
Precisely. So Gervish hypothesized the rays were likely ultraviolet or shorter wavelength. Since they promoted mitosis cell division, he called them mitogenic rays.
And was he the only one who found this?
No, the book highlights that numerous other respected scientists before and after him claimed they successfully replicated his results in labs across Moscow, Paris, Berlin. Some even reported measuring this radiation with modified Geiger counters sometimes.
But not everyone could replicate it.
True, not every lab got consistent positive results, but the fact that multiple independent teams did report positive findings gives his initial work some weight.
And this led to bigger ideas, like a bioenergy field.
Exactly. It contributed to this broader concept of a specific biological energy, a bioenergy field associated with all living things, often thought to be electromagnetic, maybe visible under certain conditions, linked to metabolism, health.
Like concepts in Eastern medicine, chi, prana.
Very similar ideas. Many ancient Eastern systems have philosophies built around this core concept of a vital life energy.
The book then goes back even earlier to Carl Reichenbach, who we mentioned right at the start.
Right, Reichenbach. Half a century before Gervish, he was investigating what he called odal, or the odic force. He found certain people, whom he called sensitives, seemed able to perceive some unknown force or energy around magnets, crystals, and, significantly, all living things.
Sensitives, what did they perceive?
He did tons of experiments, often with young women experiencing neurasthenia, sort of fatigue and other symptoms. They consistently reported seeing faint, colored emanations or auras around magnets and crystals in total darkness.
Auras. That sounds out there.
It does to modern ears. Reichenbach even documented instances where a powerful magnet near an unconscious sensitive person reportedly seemed to stick to their skin, defying conventional physics.
Okay. Then fast forward again to Walter John Kilner.
Yes, Kilner. An English physician, about 50 years after Reichenbach, he was interested in electrical treatments and started experimenting with special glass screens coated with a dye called dissonance.
Dissonance screens. What did he do with them?
He claimed that by looking at people through these screens under specific lighting, he could perceive the human atmosphere, a faint, hazy, often colored outline or aura around the body.
Another aura claim. Did you think it was useful?
He proposed that the aura's characteristic size, shape, color could potentially be used diagnostically to assess someone's physical or even mental health.
Okay. Then the book gets into Wilhelm Reich and orgone energy. That's a really controversial one, isn't it?
Extremely controversial and ultimately tragic. Reich believed passionately in this universal life energy, orgone, contained in microscopic vesicles he called bions. His theories, especially linking orgone to sexuality, psychology, bioenergy, generated huge controversy.
And got him into trouble.
Big trouble. He clashed directly with the scientific and medical establishment and eventually the U.S. Food and Drug Administration, FDA.
What did the FDA do?
They got a court injunction ordering all references to orgone energy be deleted from his books and papers, including his influential works on psychotherapy. Shockingly, the FDA interpreted this as a mandate to physically destroy all his books mentioning orgone.
Book burning. Sir,
Public book burnings. Reich refused to comply, was imprisoned for contempt of court, and tragically died in federal prison. A really dark chapter.
Wow. That reminds me of 2020. Okay, slightly less dark, maybe. Kirlian photography. What's that?
Kirlian photography, a unique technique capturing striking, often colorful images of objects' leaves, fingertips when they're placed in a high-frequency electrical field.
And the phantom leaf effect.
That's the really intriguing part that sparks debate. You take a Kirlian photo of a fresh leaf, then you cut part of the leaf away, or even remove it entirely after the first exposure. Sometimes a second Kirlian photo still shows the complete outline of the original whole leaf.
A ghost image of the missing part.
Essentially, yes. It's led some researchers to speculate about a morphogenetic field, like a non-physical blueprint or organizing principle for the organism.
What do skeptics say?
They often argue it's just recording secondary electrical discharges, moisture patterns, or other conventional effects, not a distinct biological energy field. But that visual phantom leaf in documented photos remains pretty enigmatic, hard to dismiss easily.
And Kirlian himself faced ridicule.
With a familiar pattern, ridicule, professional ostracization, yet his intriguing results are still discussed.
So all these different investigations into biological entities, biofields, mitogenic rays, auras, while often outside the mainstream, they collectively raise these really fundamental questions about life, energy, and interactions our current science might not fully grasp.
Exactly. They challenge us to keep an open mind about the possibility of subtle yet significant energetic processes within and around living organisms that we don't yet understand.
Okay, let's shift now to something increasingly recognized, but still complex. The mind-body connection, and how it relates to alternative or complementary therapies.
The book points to a surprising early clue. Astronauts returning from space showed measurable changes in their immune systems, initially blamed just on physical stress.
But it sparked more research.
Exactly. Into how psychological and emotional factors affect our physical health right here on Earth.
And they found links.
Yes. A significant Australian study in The Lancet looked at recently bereaved spouses. They found a measurable dip in their lymphocyte function, a key immune system marker right after their loss, compared to a non-bereaved group.
So severe emotional stress directly impacted their immune systems.
That's what the evidence strongly suggested. Now, the precise mechanisms, the biochemical pathways, the neurological links and connections to specific diseases are still being actively researched.
It's complicated.
Very, but the accumulated evidence consistently points to this substantial, often underestimated link between our mental and emotional states and our physical health.
The book mentions studies linking personality and stress to risk of death from cancer or heart disease, even more than smoking sometimes.
Some studies suggest that yes, and even hints that different personality types might be more susceptible to certain diseases. It's complex, correlational mostly, but intriguing.
And there was that Lancet study on breast cancer patients receiving psychotherapy and self-hypnosis.
A remarkable study. The group getting psychological help alongside conventional medical treatment survived significantly longer average of 3 years compared to the control group getting only standard medical care, who averaged just 18 months.
Double the survival time, on average. That's huge.
It really suggests that psychological interventions can have a tangible, potentially life-extending impact, even in serious illness.
The book then looks at things like acupressure.
Right. Often viewed skeptically by conventional medicine, but the book details a study in the Journal of the Royal Society of Medicine. Applying acupressure to a specific point near the wrist, the P6 point significantly reduced morning sickness in pregnant women compared to both a sham treatment and no treatment.
Just pressing a point on the wrist.
Apparently so in that study, and it wasn't isolated. The same team reported similar positive results in other trials published in respected journals, showing acupressure and acupuncture helped reduce nausea and vomiting after surgery and from chemotherapy.
So consistent findings across different conditions.
Yes, and separate trials also share efficacy for post-op vomiting specifically.
What about lifestyle changes? There's that U.S. trial.
Yes, the groundbreaking trial also published in The Lancet. It showed that comprehensive lifestyle changes, very low-fat vegetarian diet, quitting smoking, stress management techniques, moderate exercise, could actually reverse established coronary heart disease.
Not just slow it down.
Reverse it. Which contrasted sharply with the control group getting conventional care like cholesterol drugs or bypass surgery.
Wow. And Dr. Ashley Conway's review of hypnotherapy for cancer.
Conway, a Harley Street psychologist, reviewed the literature. He acknowledged the challenges in doing perfect research here, but concluded that things like hypnotherapy likely offer significant benefits for managing cancer symptoms, improving quality of life.
And he had a view on why this area is maybe overlooked.
Yes, he felt major, potentially fruitful research areas on the mind-body link are often ignored or underfunded because of the dominance of a purely mechanistic, reductionist paradigm in orthodox medical research. Looking for the drug, the surgery, not the holistic picture.
It really makes you ponder all the unanswered questions, doesn't it?
Yeah.
Like, how does the placebo effect actually work physiologically? Why do some people have spontaneous remissions? What's the full impact of psychological interventions?
And the book points out how hard it is to get funding for this kind of research, often because it focuses on prevention or well-being, not the magic bullet drug cure, and partly because some of these areas are still, unfortunately, a bit scientifically taboo.
Why the reluctance from funding bodies? Just the focus on cures over prevention.
That's a big part of it. The historical bias in Western medicine towards drugs and surgery, treating illness rather than preventing it, plus avoiding areas seen as unconventional. It means potentially significant, even life-saving research avenues might just get neglected.
Which brings us right back to that critical point the book makes, the taboo around scientific dissent, around investigating ideas outside the consensus.
Exactly. The book argues compellingly that just the perceived penalty for researching taboo areas can have this powerful chilling effect. It might stifle truly important discoveries. The example given is using biological electrical fields for early disease diagnosis may be hindered because it's seen as unconventional.
And the territorial taboo, scientists guarding their turf.
Yeah, where established scientists in a field actively discourage outsiders from commenting or writing on their subjects. The often hostile reaction from fusion researchers towards the electrochemists involved in cold fusion is cited as a prime example of that stay-in-your-lane mentality.
But history is full of successful outsiders, isn't it?
Absolutely. The book reminds us. The Wrights, Edison, Darwin, Dalton, even Fleischmann and Pons recently. These examples powerfully counter the elitist idea that only insiders can make big breakthroughs.
Maybe one of the worst parts of the taboo is how it becomes permanent. The cumulative discriminatory effect.
That's a really insidious aspect. Once an idea is labeled suspect or against the paradigm, it tends to stay dismissed. And tragically, the very fact it was rejected before becomes the justification for rejecting it again. It's a self-reinforcing cycle of exclusion.
Can peer review contribute to this, even though it's meant to ensure quality?
It can, inadvertently. Peer review committees are often made up of scientists invested in current orthodoxies. This can lead to bias against research challenging those views. It's one reason privately funded research on taboo subjects often happens in these under-resourced, low-visibility skunkworks, with limited ways to get published in mainstream journals.
And this reluctance spreads to the media, too. Broadcasters shy away.
Often, yes. Despite tackling contentious political or social issues, TV and radio producers frequently hesitate with scientifically taboo subjects, mostly fearing backlash, criticism from the orthodox scientific community.
The book mentions the greenhouse conspiracy controversy.
A stark example. That UK TV program questioned the consensus on climate change. The controversy around it and its rejection for broadcast in the U.S. highlights this potential for scientific censorship in media.
And there's a difference between the U.S. and UK approach.
The book points out the U.S. has constitutional free speech guarantees, so debates can happen more openly, even in Congress. In the UK, it's sometimes treated more as a private matter for the scientific establishment, potentially leading to more self-censorship by media.
Even something like evolutionary biology is treated as taboo in UK schools and media. Only the standard Darwinian view allowed.
The book notes that, contrasting it with the old Soviet Union, surprisingly, where there was apparently a primetime TV debate on Darwinism sponsored by their Academy of Science, suggests maybe more public openness there, ironically.
Why are media so hesitant? Just fear of being labeled unreliable?
That seems to be a big part of it, fear of being called crankish if they give serious, unbiased airtime to ideas far outside the accepted scientific story. But also, pharmaceutical advertising is a large part of their revenue. So the potential opportunistic incentives for suppressing alternative views or even outright manipulation of the narrative are very high.
It really paints this complex picture, doesn't it? All these factors making it incredibly hard for genuinely new, potentially revolutionary ideas to get a fair hearing.
It truly does. And this resistance often rests on this underlying, often unstated belief in the myth of linear, continuous scientific progress, mainly driven by big, publicly funded institutions.
But the book challenges that myth head-on, right?
Right.
Asking how often major breakthroughs really come from those institutions versus the derided loners.
Exactly. It poses that pointed question. And a quick, maybe superficial look back at the 20th century's big innovations reveals a surprising trend often favoring the lone wolf.
Like what?
Telephone, turbine engine, practical light bulb, radio, powered flight, cars, movies. Many are largely credited to individual inventors, not huge institutional projects.
So while institutional science is vital for basic research, atomic physics, astronomy, sure.
The book argues the often caricatured lone eccentric has arguably had a much more direct, tangible impact on our daily lives, which naturally raises big questions about the efficiency and impact of the vast sums of public money poured into R&D.
Billions are spent annually.
In the early 90s UK, over £5 billion a year, a huge chunk of the budget. And focusing on medical research, which gets a lot of that, the book points out something sobering.
What's that?
Life expectancy at age 45 in the UK hadn't actually improved much since the early 20th century. The overall increase in average lifespan, mostly due to better hygiene, antibiotics, lower infant mortality, not necessarily huge breakthroughs from recent publicly funded medical research.
That's quite a statement. No major improvements in disease or death rates from public funding in the decades before the book was written.
The book suggests that for the 20 years leading up to the mid-90s, substantial improvements in morbidity or mortality from major diseases directly attributable to publicly funded research were limited. Key advances like beta blockers, ulcer drugs, often came from individuals in the pharmaceutical industry, like Sir James Black.
And cancer rates were increasing despite massive research funding.
That concerning trend is highlighted. It quotes figures like Dennis Burkitt and Robert Sharp criticizing the misdirected focus of cancer research, the underfunding of prevention, and it notes the UK's NHS played a surprisingly small role in direct medical research then.
So the book suggests big changes to science policy.
Yes, more end-user involvement, patients, public, in setting priorities, shifting funds towards prevention, getting the NHS more involved in research. The core argument: the dominant model of public institutional science might not be the most effective way to drive truly impactful progress. And this resistance isn't just about funding or institutions. It's deeply tied to our psychology, how we process information, how we react when our beliefs are challenged.
The playing card experiment, that's a classic. Tell us about it.
Bruner and Postman's experiment, they made decks with anomalies like a red 6 of spades, a black 4 of hearts, showed them to people for longer and longer times.
And what happened?
Extraordinarily, even with plenty of time to see the weird card, most people unconsciously normalized it. They saw the black 4 of hearts as either a normal red 4 of hearts or a normal black 4 of spades.
Their brains just corrected it to fit what they expected.
Exactly. Filtered out the conflicting info to fit their existing mental boxes for playing cards. A powerful, unsettling demo of how much our expectations shape perception. We see what we expect to see,
Even when the evidence contradicts it.
Right. And this connects to Leon Festinger's theory of cognitive dissonance.
That feeling of discomfort when new info clashes with our beliefs.
Precisely. The book cites a poll on smoking and lung cancer. Heavy smokers were way more likely to deny or downplay the scientific link than non-smokers, reducing that uncomfortable dissonance.
And people handle dissonance differently.
Yes. Some have a low tolerance for it, go to great lengths to reduce the discomfort, maybe rejecting the new info or even attacking the source. This relates to the concept of the authoritarian personality, more rigid thinking, intolerant of ambiguity, quick to dismiss challenging views.
So this psychological resistance is a big factor in how new scientific ideas are received.
A huge factor. And Thomas Kuhn's work on scientific revolutions adds another layer with the idea of paradigm shifts.
Fundamental changes in how a whole scientific field thinks.
Exactly. Kuhn uses Herschel's discovery of Uranus in 1781 as a classic example. For decades before, astronomers had seen Uranus, but they always logged it as just another faint star, fit the existing paradigm.
Until Herschel realized it moved differently.
Right. That triggered the paradigm shift, realizing the solar system was bigger than they thought. It prepared them to see other unexpected things later.
It's that seeing what you expect thing again, like X-rays.
Another great example from the book, Roentgen discovers X-rays in 1895. But scientists have been playing with cathode rays for years. It's highly likely many produced X-rays without recognizing this new radiation. They didn't expect it.
It took Roentgen's accidental observation of a glowing screen.
Yes. And even then, the great Lord Kelvin initially dismissed it as a hoax. Shows the power of existing beliefs.
The book also mentions outsiders sometimes see things more clearly, like Dalton in chemistry.
Right. Dalton, originally a meteorologist, revolutionized chemistry with atomic theory, partly because he came at it from a different angle, how gases mix not the dominant chemical affinity paradigm, a fresh perspective.
Kuhn's point is that these shifts aren't just about new facts, but new ways of seeing the same facts, like Galileo versus Aristotle on the pendulum.
Perfect example. Both saw a weight swing, but Galileo's revolutionary understanding came from his genius for perception, shaped by a different intellectual background, a new way of framing the question.
So it's not just the data, It's how we're conditioned to interpret it through our existing beliefs, our scientific frameworks. Makes accepting revolutionary ideas really, really hard.
Fundamentally challenging. And the book goes even deeper into the specific social and psychological games played within the scientific community itself.
Like the research game, Dr. Ashley Conway's idea.
Yes. Conley describes this as unspoken strategies used by what he calls type 2 experts. People more concerned with maintaining their status, preserving the status quo in their field, than chasing truly innovative, potentially disruptive research.
What are the rules of this game?
Conway lists several. Prioritize methodology over actual practical significance. Avoid totally new, uncharted fields. Discourage useful outside applications. Maintain detached objectivity that maybe masks a lack of real curiosity. Suppress enthusiasm for novel ideas.
The goal being.
Minimize personal and professional risk. Keep your comfy position in the hierarchy.
And the book gives an example, Dr. Paper and the asthma treatment.
Right. Pieper, a type 1 expert focused on results, developed a seemingly successful non-drug asthma treatment. But instead of enthusiasm, he reportedly faced skepticism and petty criticism from type 2 experts.
He focused on minor technicalities to dismiss it.
Exactly. Seemingly more worried about upholding the dominant paradigm than exploring a potentially helpful new treatment.
The book even references C.S. Lewis's That Hideous Strength.
Yes. The character Mark Studdock, seduced by wanting to be in the inner circle of an elite scientific institution. It highlights that very real human tendency to devalue, even attack, work done by outsiders who challenge the establishment.
A fictional example,
Yeah.
but it resonates with real social pressures in science.
It does, though the book thoughtfully contrasts Studdock with the real scientists of the Manhattan Project, their intense dedication to a shared high-stakes goal. It also recounts the competitive, emotional race between Watson and Crick and Linus Pauling over DNA structure. Science isn't purely rational.
So it's this complex mix, seeing what we expect, reducing dissonance, fitting data into paradigms, authoritarian traits, the research game, wanting to belong to elite groups, devaluing outsiders.
All these human tendencies contribute to the resistance new ideas face, which begs the question, given all that, how does anything new and revolutionary ever break through?
A very good question. And the book then looks at the gatekeepers, the taboo enforcers, the people and institutions who can promote or suppress unconventional ideas.
The backlash against Immanuel Velikovsky's Worlds in Collision, even before publication, is a prime, maybe disturbing example.
What happened there?
Prominent scientists, many admitting they hadn't even read it, issued these scathing public denunciations, tried to kill it before it even got out.
And it wasn't just words.
No, Macmillan, the original publisher, faced serious commercial pressure. University professors threatened boycotts, stop buying any Macmillan books if they published Velikovsky.
Wow. Did Macmillan cave?
They did, forced to cease publication, even though it was becoming a bestseller. Doubleday eventually took it over, and the editor at Macmillan who first championed the book reportedly fired.
That's intense. But didn't some of Velikovsky's seemingly crazy predictions turn out to be right?
Some did seem borne out later by spacecraft observations. Venus's high temperature, its retrograde rotation, Jupiter's big magnetic field reaching Earth's orbit. And there is that amazing coincidence with astronomer V.A. Bailey finding the sun's surface potential was almost exactly the value Donald Menzel had used to try and disprove Velikovsky.
Yet he was still dismissed.
Largely, yes. Mainstream science mostly continued to label it pseudoscience. Scientific American refused to advertise his book.
The book also looks at how scientific journals handle taboo subjects, like Nature and the Puthoff-Targ paper on parapsychology.
Right. It suggests the choice of referees might sometimes be strategic. In that case, a known skeptic with limited specific expertise in parapsychology was chosen to review their SRI work.
To ensure a negative review.
The book implies that possibility. It also talks about coded language in reviews, subtle signals to those in the know that findings should be viewed skeptically, even if the paper gets published.
And how prominent figures address alternative therapies, maybe relying on orthodox opinions rather than talking to users.
That potential bias is noted relying on establishment views rather than direct engagement with people who've used the therapies and might have benefited.
What about Dr. John Taylor? The physicist who studied Geller was initially positive, then completely reversed his opinion.
A perplexing case. He witnessed phenomena that seemed to defy conventional explanation, yet later did a complete U-turn. Illustrates the complex pressures scientists can face when investigating these areas.
And then there are direct attacks, like Dr. George Price accusing ESP researchers Ryan and Sol of fraud.
Unsubstantiated accusations, which Price himself later publicly retracted and apologized for,
Yeah.
it highlights that damaging tactic. The book also introduces CSI COP, Committee for Skeptical Inquiry.
Their goal is critical investigation of paranormal claims.
That's the stated aim. But the book points out they largely don't conduct or sponsor their own primary research, and it critiques the approach of some members, like Professor Hansel, who seem to think hypothetical fraud scenarios were enough to prove fakery, even against evidence, like in the Duke ESP experiments. Their focus tends to be debunking, not necessarily open-minded investigation.
And COPIS, the UK Group for Public Understanding of Science.
Committee on the Public Understanding of Science funds local science initiatives. The book suggests even there, sometimes a subtle egoism reinforcing established science's superiority might influence funding choices.
So it's this complex landscape where biases, institutional pressures, protecting paradigms can all get in the way of unbiased inquiry into new, potentially transformative ideas.
Exactly. It makes discerning truth from error incredibly difficult, especially with anomalous phenomena.
Which brings us to that fundamental challenge. How do we tell real from unreal, especially in these murky areas?
The book revisits specific Geller demos at SRI, the 1 in a million die result, influencing the scale without touching it, stressing these observed events need explanations beyond just dismissal as trickery.
It also mentions Lord Clancarty's claim about holes at the Earth's poles based on NASA photos.
Right, maybe a flawed interpretation, but the point is, if a claim is based on some perceived evidence, it deserves a reasoned response, not just being labeled crank.
The cautionary tale of blonde lot and N-rays is important here, isn't it? Seeing effects that weren't there.
A stark reminder of self-deception. The visiting scientist, Robert Wood, secretly removed the key prism from Blondlot's N-ray device, but Blondlot and his team kept seeing the N-ray effects, permanently discredited him.
Which leads to Irving Langmuir's concept of pathological science.
Yes, Langmuir, a Nobel laureate, coined that term for when respected scientists unintentionally fool themselves into believing they found something new that turns out to be illusory.
And he had symptoms for it.
He did, like barely detectable cause, effect near the limit of detection, claims of great accuracy, fantastic theories to explain it, ad hoc excuses for criticisms, and a typical rise and fall in supporters.
The book applies these criteria to several historical cases.
Yes. The Davison-Barnes experiment on alpha particles, the inconsistent mitogenic ray reports, the discredited Allison effect claiming new elements.
And maybe most surprisingly, even Millikan's Nobel-winning oil drop experiment, the one that measured the electron's charge.
Even that one. The book examines Millikan's own lab notes, suggesting a somewhat selective approach to data favoring results matching his theory, maybe downplaying or excluding ones that didn't fit neatly.
So Millikan's work showed some symptoms of pathological science.
Arguably, yes, according to the book's analysis using Langmuir's criteria. Effect near detection limit, claims of great accuracy, lots of trials with apparent data rejection, ad hoc explanations. It fits many symptoms. Except the crucial last one, its eventual widespread and lasting acceptance by the scientific community. Which highlights a key point. Acceptance isn't always based purely on objective evidence alone. Consensus, persuasion, reputation play roles.
So given all of complexity, how should we approach weird, anomalous stuff? The book mentions Dr. Peter Sturrock's guidelines.
Yes, Sturrock, an astrophysicist who studied controversial claims, proposed some useful guidelines. Things like face the strongest evidence for the phenomenon, go to original sources, deal in degrees of belief, probabilities, not absolute yes-no, focus on evidence and testing, working teams, list all your assumptions clearly.
Good practical advice.
Very. And the book reiterates that history lesson. Acceptance of revolutionary stuff like powered flight, or even contested claims like cold fusion, was driven by the discoverer's persistence, not immediate scientific embrace or purely rational debate within existing paradigms.
Which makes you wonder, how many other important discoveries got lost because the researchers weren't persistent enough or couldn't get attention, especially when the early evidence seemed weak?
A critical and unsettling question. The book suggests maybe weak initial evidence doesn't mean something's unreal, just that our current techniques or understanding aren't good enough yet to see it clearly.
Like early versions of things that seemed useless but became vital later.
Exactly. Maybe illness diagnosing black boxes, faint mitogenic rays, dowsing signals. They might just need amplification, better methods. The scientific method alone, as currently practiced, might not be able to definitively rule them out early on.
Karl Popper's philosophy comes in here too, that even established theories are provisional.
Right. Even Newtonian dynamics could be challenged. The book notes that shift in science from a quest for truth, maybe towards a quest for certainty and prediction.
And the gap between empirical facts and the whole body of scientific belief, the book calls it the myth of science.
A provocative term, cautioning against arrogance if our understanding is maybe more like evolving shadows of a deeper reality.
The book also touches on scientists' responsibility for how their discoveries are used, like the Paris gun in WWI.
Yes, the ethical dimension. And the cautionary tale of Thomas Midgley Jr., inventor of leaded gasoline and CFCs. Well-intentioned science with devastating unintended consequences.
A contrast is drawn between pre-WWII government protecting citizens, air raid plans, and a post-war shift to scientific government, maybe diminishing direct responsibility, favoring rational justifications.
That perceived shift is noted, along with a growing intolerance for academic and scientific dissent in modern science.
And a loss of that Enlightenment optimism, where science and politics promise a bright future.
Yeah, a sense that each wave of discovery, while promising control, ultimately reveals nature's unpredictability. Even microbiology, genetic engineering, the book, critiques the view that they give us complete control over life is maybe oversimplified.
Wilder Penfield's brain mapping experiments are used as an example,
Yeah,
showing complexity even where we think we understand things.
exactly. Mapping speech areas revealed the mind's profound complexity, limitations of purely mechanistic explanations.
And accepting new ideas often relies on a subjective feeling of irresistibility, influenced by our existing beliefs, our mental autopilot.
Right. Not just objective evidence. The resistance to the Gauquelin's statistically significant astrological findings, planetary positions correlating with sports champs, is an example. Despite the stats, it felt wrong, didn't fit the worldview, even though it wasn't inherently stranger than some accepted science.
And finally, David Hume's problem of induction. Past observations don't guarantee future ones.
A fundamental challenge. Science can't prove something impossible today will always be impossible.
So the book suggests resistance to anomalies might stem from a kind of superstitious belief in a rational universe, a fear of scientific anarchy if paradigms fall.
Possibly. It emphasizes how unproductive fraud accusations are without concrete proof, citing Paul Kammerer's case, the backlash against his experiments suggesting inheritance of acquired characteristics, including fraud claims despite photos. Better to assign probabilities, stay open-minded.
Not absolute acceptance or rejection.
Exactly. The final conclusion is pretty bold. There are numerous major anomalous phenomena orthodox science is largely ignoring or resisting, but they deserve careful, unbiased study and could lead to radical revisions of how we see the world.
It's really a powerful call for intellectual humility, isn't it? A reminder that chasing knowledge needs rigor, critical thinking, and the courage to look beyond the comfortable boundaries of what we think we know.
Beautifully put. Humility and courage.
So there you have it, fellow deep divers. We've journeyed through this fascinating, often contentious landscape of scientific resistance, looked at amazing innovations initially dismissed, explored the tricky psychology and sociology of science, and wrestled with telling truth from error. You, our intrepid listener, are now, hopefully, armed with a richer, more nuanced view of these ongoing challenges to the scientific establishment.
And maybe, just maybe, the biggest breakthroughs of the future won't come from the billion-dollar projects, but from revisiting those impossible ideas with fresh eyes, better tools, and truly open minds.
Yeah. What common sense beliefs might we be clinging to right now that are blinding us to something profound?
That's the question to ponder.
It truly is an awe-inspiring thought. We really encourage you to keep exploring these themes, think about your own biases, stay open to the genuinely unexpected. Thank you, as always, for sharing your curiosity and going on this mind-expanding adventure with us.
Yeah, thanks, everyone.
Until our next deep dive, keep questioning, keep exploring, and keep that mind wide open.